Today we are jumping into this idea of combining random variables. So what we're getting into today, and this is a weird way to say this, but you'll kind of start to see it as we get into this a little bit more. We're getting into the algebra of statistics. But don't get too excited yet, because it's not algebra. In the algebra of statistics, and we're going to actually look at this on Friday a little bit, x plus x does not equal 2x. In statistics. Okay, so what we're doing is we're going to start transforming and combining random variables. So before we get into that, first of all, let's go back and talk. What is a random variable? It's a chance process that has set outcomes with probabilities associated with the outcomes. You guys did this last class with a continuous random variable with a normal curve, right? Before that, we had worked with discrete random variables, like number of children in your family where there was a countable outcome, right? What we're going to be talking about today is this scenario here, where you've got a new job, and your hourly rate is randomly assigned to you each day you go to work, based off of this probability distribution. You could earn $1 an hour, $5 an hour, $7 an hour, $10 an hour, $15 an hour, $25 an hour. So get out your calculator. And go math, probability, random number generator, math, probability, random int. Our lower bound is going to be 1 and your upper bound is going to be 100. How much money are you making? Tristan, what'd you say? What number did you get on your calculator? You got 34, so you're in this category. By the way, I'm doing this intentionally. What am I forcing you to review by doing this? Yes, but bigger than, more important than that. What did we just talk about? What is this process right here called, where we give numbers to an outcome? It was in chapter 5. And a lot of you struggled with this in chapter 5. That's why I'm doing it right now to review it. What's it called when we let numbers represent different outcomes and then we generate it on our calculator, or we generate it with software, or whatever? It's called a simulation, because we're simulating your job, right? We're not actually going to the job and picking out how much money you make, are we? We're simulating this, and how are we simulating it? We're letting numbers represent our various outcomes and generating that from your calculator. Simulation, okay? I'm reminding you of that because it will show up again. We're going to do simulations later on in the year as well, so I want to make sure you remember that. Now, I heard somebody call out, somebody else. Did anybody get $25 an hour? You did? What was the number that came up?
98.
98. Got $25 an hour? You got 100. They got $25 an hour? You guys are feeling pretty good. Yeah? Making $25 an hour. Did anybody get $1 an hour? Carter did? You're not feeling very good about this job, are you? $1 an hour, you wouldn't want to go to work very much for that. But you don't know how much you're going to make until you actually get to work and work. Okay, so that's kind of a bad deal for you on that day. Is it going to be the same every day? No. Every day you go into work, you're going to do this again and figure out how much you're going to make for that particular day. It's going to change every day. Go ahead and copy. Well, first of all, I've got to get my paper. Where's my paper at? We need to figure out what is the probability of each one of those outcomes. So how likely is it to make $1 an hour? What's the probability of getting $1 an hour? 15? That's the easiest one. What's the probability of making $5 an hour? I hear 16 and I hear 17. You say 16? Carter, you say 17? Why are you saying 17, Carter? Because there's 17 values. You have to count the 16, you have to count the 32. There are 17 values. Let me show you a simpler version of this. Rather than doing 16 and 32, I'm going to say it's like 4, 5, 6, 7. How many values are there? There are 4. There are 3 differences. There are 4 values. Counting principle is not something we're really working on in this class much. But when we subtract them, 7 minus 4, what we're finding there is how many spaces are there. How many differences are there? There's 3 differences. That's why we use the word difference when we talk about a subtraction problem, because there's 3 differences, but there are 4 values there. Okay? So, what's the probability of getting to $5 an hour? $5 an hour. Yeah. Now, what's the probability of getting $7 an hour? I get 28. 0.28. What's the probability of getting $10 an hour? $15 an hour. And 105. Is this a valid probability model? How do we know? Adds up to 1. Again, review of that concept. Now, you go to work. You work there for several years. How much on average do you make? I'm asking you to find it. Calculate and interpret the expected value of x. What does the expected mean? Mean or average. Kevin gets $8.21. Anybody else agree? Yeah. I also agree. So, the mean amount of money you're going to make is $8.21. Now, common mistake that a lot of kids make is they simply say 1 plus 5 plus 7 plus 10 plus 15 plus 25 divided by 6. How come we can't do that? How come we can't simply add these numbers together? Doesn't account for the frequency of them, does it? 1 doesn't occur equally often as 5 does. So we have to weight those frequencies, right? How do we do that? What's our shortcut way for this? I saw a lot of you doing it. 1 bar steps. This goes into list 1. This goes into list 2. 1 bar steps. I should be writing this on my paper now. Brindley, when you're watching this, sorry, I'll copy it onto the paper so you can see it. And for anybody else that maybe wants to watch this later. By the way, everybody say hi, Brindley. Brindley's recovering from surgery. Yeah, so that's why she's not here. All right. Hi, Brindley.
Hi, Brindley.
Got to make sure you tell her that we did that, right? All right, how do we interpret that? What would we write to interpret that? What does that number mean? You're on the right track. Be a little bit more technical with it. You're right. If we go to this job several days, or repeatedly, right? We go to this job and do this over and 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 over again, we can expect to earn $8.21 an hour. Kind of that template of what it means to be an average, what it means to be an expected value for a random variable. What about the standard deviation? What did you say? I didn't hear you. 5.43. And what does that number tell us? What do we know about that? What's that number tell us? Will vary by about $5.43 from the mean. So on a typical, quote-unquote, typical day, you can expect you're going to average out to earn $8.21. That number could be, you expect it to be varying by as low as $3 an hour, roughly, up to maybe as high as $13 an hour. How many of you would take this job? No? There's a chance we're not going to make very much money, right? Is there also a good chance that we can make decent money? Not a very good chance. Don't want to take that chance. All right. Random variable. This is all review from 6.1. Are we okay with that? Now, the new stuff. We're going to come back to this in just a second. The new stuff. Now we're going to transform it, and eventually we're going to combine them. But we're just going to talk about transforming for right now. First, though, let's go back to chapter 2 and transform just a distribution. What happens when we add or subtract a number from every single number in the distribution? The whole distribution moves left or right. What changes? When we add or subtract, what changes? The mean, as well as any of the other locations, right? The min, the max, the first quartile, all the locations change. Does the standard deviation change? The same exact thing is true for random variables. When we add and subtract, we're only changing the mean. The standard deviation does not change by adding and subtracting. What about multiplying? If we take a distribution and we multiply every single value in that distribution by 10, what changes? Everything changes by that same factor, doesn't it? Doesn't the standard deviation also now change? Because now the numbers are 10 times as far apart, right? Everything is spreading out much farther. So, multiplying or dividing impacts the mean, but it also impacts the standard deviation. It impacts both. Now, how do we apply that? How do we transfer that to algebra with random variables? If this is my distribution, this looks a little bit weird, and we'll kind of start to make sense of this as we go through this. If this is my distribution, what type of a transformation is A? What am I doing with this value of A? We're adding or subtracting. That's just shifting it left or right. So what does this number impact? Only the mean. Only the mean. It's the x values, yes, But I'm talking about from the distribution as a general. Which values in the distribution, which statistics are changed? Only the mean is affected by A. What about this value of B? What are we doing with this value of B? Multiplying. What does B change? What does multiplying change? The mean and the standard deviation. So we put this into what we call a linear transformation. This is a linear transformation. Adding, subtracting, multiplying, or dividing is a linear transformation. Here's what it looks like in actual practice. My new mean, you may want to write that over the top of this. This is my new mean, is going to equal to my old mean multiplied by whatever B is and added or subtracted by whatever A is. So, my new mean is equal to my old mean multiplied by whatever B is and added by whatever A is. What about my standard deviation? My new standard deviation, does A affect the standard deviation? No. So you'll notice that my old standard deviation is only impacted by B. Whoops, I didn't want to circle that. Why is that in the absolute value? Standard deviation can only be positive. So if B happens to be a negative multiplier, the standard deviation is still positive. Keep that in the back of your brain, because we're going to come back to that later. Standard deviation always has to be positive. Anybody remember why? Can't have negative distances. Standard deviation is the average distance from the mean, and we can't have a negative distance. So standard deviation is always positive. So that's why that absolute value is on there. Now, we're going to experience that. Everybody got all that copied down? On your dream job worksheet, we're going to look at both types of transformations. I'm going to give you, we get out of here at 1:30, right? Give you guys 10 minutes to do 1 and 2. Shouldn't take you very long. Do 1 and 2. All right, so how many of you went through and retyped this into list 1 and list 2? There's nothing wrong with that. There's nothing wrong with that. My goal, though, is not to make you do that much work, because that takes a lot of extra time, right? Instead of retyping this into list 1 and list 2 and doing one-bar stats, what's the shortcut? If we're adding 10 to all of them, we're just simply adding. What changes when we add? Only the mean changes when we add. Did the standard deviation change? Those of you that did it on your calculator, did the standard deviation change? So, did we need to even do this on the calculator? We could get to this answer without having to do any calculator work. Okay, what about when we turn the page and we do the multiplication? So here, it's going to be 2, whoops, not 20, 10, 14, 20, 30, right, Kevin? And 50. The mean is going to be 1642, and the standard deviation is going to be 1086. Again, did we have to put this into the calculator to find this? All we really needed to do is take our original distribution and multiply it by 2 to connect that idea back to what we started with back on the first page. How can I find my new mean? If it's adding, I add it to the old mean. If it's multiplying, I multiply it by the old mean. What happens if we do both add and multiply? Let me rephrase that. What happens when we do both add and multiply? We have to do both of them. Which one do we have to do first? Multiplication first because order of operations. Multiplication comes before addition. On standard deviation, adding doesn't affect the standard deviation, so we don't worry about adding. It never changed it. Multiplying does change the standard deviation, so we could have just multiplied by 2. Everybody okay with that? All right. So, interesting conversation here with number 2. Whoops, let me get here. Which option would you, as an employee, prefer? Option A or option B? I want to hear some of your thoughts. Kevin, what did you say? On average, you'd make more. You'd have to be at that job for a long time, probably, right? In order for that to really pan out. On average, in the long run. Okay? Jaden?
But 40% of the time, if you're on that top half for multiplying, you'd be making more money in the long run as long as you can stay in.
So are you a little bit of a gambler?
Yeah,
Yeah.
as long as you stay in that top 40%.
Okay? The doubling, this is a whole lot more than any of this adding 10 is. That's what you're getting to, right? Yeah. Kevin?
I choose option A because even the lowest amount on option B is $2, but on A it's 11.
You're guaranteed to be, no matter what, you're going to make more.
Yeah.
If you're at the bottom end of it. Okay? By the way, this principle that we're talking about right here, we have fun with it while talking about it as an employee making money at a job. Hopefully, I really do hope all of you eventually someday invest money into a stock market or a mutual fund or things like that. This is what you have to pay attention to. When you go to look at which mutual fund to invest your money in or which stock to invest in, it's going to say the average return and how much that return varies from year to year to year, month to month, or whatever it's based off of. High standard deviations are high risk, high reward, right? You could lose a lot of money, but you could also make a lot of money. Low standard deviation is low risk, low reward. You're not going to make a whole lot, but it's pretty much guaranteed you're going to make something. That's kind of what you were just saying, Kevin, right? Now, ultimately, in the long run, what do most investors tell you should do? A little bit of all. A balanced portfolio. You should have some in high risk, high reward, some in low risk, low reward, so that you're guaranteed you're always going to be improving your financial status. All right. Reset. So that's obviously not a very good method. So instead, your boss decided on a permanent employee wages that is still based off of a random distribution. By the way, this would not really be a job that you would ever have, but we're using this just to kind of help have a little bit of fun with it. So you're randomly assigned a salary or an hourly rate, but at the end of every year, she's going to give you a raise as well. That raise is also based off of a probability distribution. Fair enough? Real quickly, Kevin, plug this in and find the mean, standard deviation, and variance. Carter, plug this in and find the mean and standard deviation for list 1 and list 2 for this one. I don't want to make everybody do that. We'll just do that real quick. You can all do the list 1 and list 2 and find that. Yes? Or very, very devious.
Oh, they can get mad at
The mean is
They get the wrong
11.85. The variance
You don't have it.
and standard deviation is 2.2.
I think it's 2.22, isn't it?
Yeah, if you round up this.
Okay.
So variance should be 4.93.
The means 1.6 and deviation is
0.92 if we rounded to dollar amount. Okay. All right, copy those down. Huh? It is burning up in here. I don't know why it's so hot. The rest of the hall doesn't like it when I open my door because I yell. That means you guys just have to be quieter so I don't have to talk as loud. Fair enough? All right.
I like that your computer on like all the Thanksgiving break, but it's just been faded.
No, it was cold in here on Monday. Yeah. All right. Let's continue on. We've introduced this new variable here. I introduced it to you all on Monday, but now we actually are going to have to use it. What is variance? What's the relationship that we've talked about with variance from Monday? So this is standard deviation. This is standard deviation squared. And it's that simple of a connection. You're going to have to be able to work back and forth with those. So what is my variance for this? And what is my variance for this one? Whoops. Now, notice that it does not have a label on it. I put a label on it and I had to erase it because it does not have a label. Why doesn't variance have a label on it? This is dollars. This would be dollars squared. Does dollars squared mean anything? Has no meaning to it, right? Variance is a measure of variability, but it is labelless. It does not have a label associated with it. This is the only section, the only time we're ever going to have to deal with variance for this class. For other statistical analysis that you'll get to later on, they do what's one process that's the next one after this class called ANOVA's, analysis of variance. And they'll actually use variances there. And then beyond this class, everything goes to variances instead of standard deviations because variance is a little bit more robust. It a little bit better measures true relationship when you get more complex with it. So you'll see why we need variance here in just a minute. But everybody okay with what's going on here? Now, look at the bottom here. After the first year, your new wage is going to be variable X, this distribution, plus variable Y, this distribution. So we're adding these two distributions together. What are all of your different possible outcomes for how much money you're going to make? What are all the different possible new wages that you could be making?
16, 12, 15.
Let's try to keep those in order.
12.
12. Where did 12 come from?
3 plus 9.
13. No?
Oh wait, no, 13.
12 plus 1.
15.
Are we okay with that? Where those come from? So those are my new outcomes here. So before we go any farther, what do you know is guaranteed to happen about variability? It's going to increase. Why do we know without a doubt before we do any math that variability has to increase? Because we have a whole lot more outcomes. We put the two distributions together, variability increases. Variability always increases. Variability will always increase. Now, be careful with this because this is a point that we're not going to mess with it today, anything, but eventually we will. What happens if instead of adding we decided to subtract? They took money away from your hourly wage. Would the variability still increase? The variability, even though we're subtracting the distributions, the variability would still increase because there are more outcomes. 9 minus 1 is 8. 9 minus 3 is 6. For every single hourly wage, you now have 2 new outcomes. So there's guaranteed to be more outcomes, whether you're add or subtract. Keep that in the back of your mind because we're going to come back to that in a minute. Now, letter B. Why? And. Going back to chapter 5, I bolded it intentionally to try to remind you. What is the probability that you got $9 an hour originally and you got a $1 raise? How do we find that probability? We multiply them. Why do we multiply it? Because it's the general multiplication rule, right? And this event and this event. Probability of A and B. So, how do I find the probability that they got $9 an hour and $1 an hour raise? I think it's 0.3 times 0.7. Because this would be the probability of $9 times the probability of $1 raise. So that's 0.21. So now I have my probability of making $10 an hour. How do I find all the rest of those probabilities? What's a tool that we learned back in chapter 5 that might be beneficial here? So that shows the multiplication that would be easy to organize all of this. The tree diagram. Down here at the bottom, you may want to draw your tree diagram to help with this. Here's my first branch of my diagram. What's my second branch going to be? Their raise. So what are my outcomes for the raise? $1 and $3 are my outcomes for the raise, right? Is that the same for every single salary? So it's the same branch here all the way across. So this probability was 0.3, 0.45, 0.25. My probabilities for my $1 an hour wage, $1 an hour raise, can't speak, is 0.7. And those stayed the same all the way across here. Is everybody following with this back? Kind of reviewing and seeing how it helps us. So finish this out. Once you have your tree diagram finished and your probability distribution filled in, go ahead and find these three values and start analyzing those three values. Are we getting close to the same numbers? All right, now let's put it all together. This process right here was fairly time consuming. What happens if instead of $2 an hour rate or 2 opportunities for raises, there was 10 opportunities for raises? All of these branches now have 10 outcomes. So now we have 30 of these. Would you want to do that with a tree diagram to find all this out? I wouldn't want you to either. So let's see if we can figure out the shortcut, because there is a pattern here. So instead of having to figure out all of those probabilities and coming up with that answer, let's see if I can get this arranged so you can analyze. This is X. Oh, she can't see that. That's X. This is Y. This is X plus Y. Right? Hourly rate, your raise, and your next year's rate based off of both of those things. What do you notice? What do you notice about the means? That one should be kind of obvious, right? If I'm adding my two variables together, I can just simply add the means. That's pretty straightforward. add the means, and I get my new mean. That's an easy one. Does it work with standard deviations, though? Doesn't work with standard deviations. Does that work with variances, though? That's why we use variances. Now, you are all familiar with this even before we ever did this problem, because you all took geometry. Yes? You all took geometry? Sigma squared plus sigma squared is equal to sigma squared. What does that sound very, very familiar to? Pythagorean theorem. That's what this is. Okay? What is the standard deviation measure? So, putting this to a visual for you so you can connect this idea. What is the standard deviation measure? In this case, it's the average distance of x, right? So the average distance of x. If we put it onto an x-axis, the average distance of x. What does this measure? The average distance of y. And what does the bottom one find? We're putting it onto a graph. So what's the relationship between my standard deviations? Pythagorean theorem. Sigma x squared plus sigma y squared is equal to this squared. Now, here's the interesting thing. Does this change if my average distances are negative and backwards? Does this change? It doesn't change. So even if I'm subtracting these numbers, what am I still doing with this one? We're still adding the variance. Remember I said earlier, variance always increases. It's always positive. Standard deviation is always positive. Variance always increases. It can never decrease. So how does all this fit back together? Turn back over to your notes. Turn the page and look at this. When we combine random variables, when we add two random variables together, to find my new mean, I simply add my old means together. That one we already knew, right? But standard deviation we can't simply add together. We have to add the variances together. Pythagorean theorem. What if we are subtracting our distributions? Well, my new mean is going to be subtracted, but what did we just say about variances? Variances are always added. Even if we're subtracting the means or subtracting the differences, my variances are always added. So when we put two distributions together, here are your two rules. Okay with that? We have 15 minutes. You have the second worksheet that you should have in front of you. This is a bunch of practice. I say a bunch, it's really only, I think, 5 problems. With this idea of random variables. Question number 1 and question number 2 are simply transforming. Question 3 is where you get, or maybe it's 4. Can't remember which one it is. One of the questions is where you're actually going to combine them. And then the last question does all of this with a continuous random variable. Don't let it trip you up. It's actually easier than what you think. This looks like a lot. It's really like 8 calculations. It should not take you very long. Most kids yesterday were able to get it finished in about 15 minutes. Okay, so go ahead and get going on that. If you get stuck, let me know. I'd be glad to help you. There is a key up here. If you want to check as you're working, you are welcome to check as you are working.